In the previous lectures, we focused more on the derivatives and the notion around the derivatives. We said that when we are talking about derivatives, we are specifically talking about the slope of a curve at a particular point, and we spent a great deal of time talking about that topic, and we also looked at the application of derivatives. When we're looking at application of derivatives, we talked about optimization, we talked about acceleration, we talked about velocity, and so many other things that are actually under the topic of derivatives. And then at some points, we started to talk about different methods that you can use to actually find the derivatives. The first principle, the product rule, the chain rule, the power rule, the quotient rule, and all those nice method, and also the method of implicit differentiation. We also looked into that, and then from there we even talked about the absolute maximum, the absolute minimum, whereby when we are actually looking at the absolute minimum and absolute maximum, there are certain steps that you need to follow. You just need to first find the turning points, and then after that, the outputs of those turning points, you actually check which one is max, which one is min, and also you check the endpoint, the output of the endpoints of a given interval, and we work well with those things. And then we also looked at some other interesting things. Today, I want us to look at antiderivatives. To talk about antiderivative, it's not difficult at all. It's just the concept of understanding that suppose you are having a function f of x, and we said that the derivative of this particular function, we usually write it as f prime of x. So this one is actually a derivative. So if this function is actually given and we know it is a derivative, then this function that is actually here, we call it the antiderivative of this particular function. That is what an antiderivative is. There's nothing more on that. Is just that if you know how to find the derivative of that, you get that. You should know the antiderivative, or what is the original function, such that if you take its derivative, you get that. That is actually the concept that I want us to actually talk about today, and take some few examples. Of course, we'll also go straight to some other nice topics in this in our syllabus. Of course, we're not going to go into deep in those things. We're just going to look at more application and how to actually find this antiderivative. I think that's all we'll talk about. And the next thing, we'll look at the meaning behind or what is actually the interpretation of an antiderivative, or what is this antiderivative, because we don't want to just calculate things that we don't know their meaning. So that is what is important when it comes to these things. So let's start with the definition. So we'll start with a definition, and I want us to define what is an antiderivative, which is simply what I just said, but I want to formally talk about it and also talk about the terms. So a function, we say a function. So we have a function. So I'm gonna use capital letter f of x. A function f of x is called, so we call this function an antiderivative. Derivative. So we call it an antiderivative on an interval. We call it an antiderivative on some interval I if we have f prime of x is just equal to f of x for all x in I. So basically here we say a function f is called an antiderivative. There's something that I needed to add here. I should have said of f of x. So this is supposed to go here. So a function f of x, capital letter f of x, is called an antiderivative of small letter f of x on an interval I, if when I take the derivative of that I get that. That is actually the meaning of this. That's all there is to this thing, antiderivative. And then we also have a theorem here. Theorem, we don't usually ask this theorem, but we usually use it. We say that if f of x is an antiderivative, it's an antiderivative derivative. So it is an antiderivative of f of x. This is a capital letter, this is a small letter, on an interval, interval I. So we have on an interval I. Then the most general antiderivative of f, on I is f of x plus c. So if let's say this f of x is an antiderivative of that on an interval I, then the most general antiderivative of f on I is given by this. In other words, this is actually the function, is just any function, because this is a constant. When you're taking the derivative of a constant, you get a 0, and then the derivative of that is going to give you that. So this one is the most generally antiderivative of this. In other words, this is a set of all functions that are actually having the derivative f of x. I hope you can see the catch here, that the most general antiderivative of this function is the set of all functions, such that when you're taking the derivative of this function, you will get this f of x. That is what is important here. And what is important here, this constant is arbitrary. It can be anything unless it is specified. We have some specifications of this. We can find that to get the specific function, but this one is the most general antiderivative of this function f of x. So what is important here is actually the terminology. So let me first write this here, where c is an arbitral. So it is just arbitral constant. So what is important about this whole thing? When I take the derivative of that, I'm going to f of x, or the antiderivative of this, or the set of all functions, such that when you're taking their derivative, you actually get this is given by this. Okay, so what do we call this c? This c here, we usually call it the constant of integration. So we have a constant of integration. And then the second thing here, remember that f, capital letter f of x plus c, we call it the most general antiderivative, or the set of all functions, such that each of these functions, when you're taking its derivative, you get that. So if you focus on only this part, this capital f of x, this capital F of x, we actually call it a particular antiderivative. So that is what we're actually having. This is called a particular antiderivative. This one is called the constant of integration, or integration constant. but the combination of those two is just the most general antiderivative. I hope you can actually see what is actually happening here. Let's look at the examples here. What are the examples? So my examples are saying one important thing here, which is saying we want to find the most general antiderivative. The most general antiderivative of each of the following. So we want to find the most general antiderivative of each of the following. So I wanted to specify something here. If the question was saying find the antiderivative, or simply let me put it like this, find a particular antiderivative, they are just saying only find this part here without the constant, a particular. That's what this thing is saying. This constant is not there, it's only this case. When they are saying the general antiderivative, the only difference is going to be we will have this and also plus some constant. That is the difference between those two things. And then another thing here, when the question is saying find the most general antiderivative of each of the following, this question is the same as find the set of functions capital letter f of x. You can also say find the set of functions capital letter f of x that have a derivative f of x. That's also another narrative. I hope I will have an example like that in the future, but for now let's just look at this. Find the most general antiderivative of each of the following. So we have a, so we have of each of the following. Let me write functions here. Functions. So I want to have f of x, and my f of x is equal to 2x. My b is going to be, I have my f of x is equal to 3x squared, and my c, I am going to have my f of x equal to 4x cubed, and then my d is going to be f of x equal to n times x raised to n minus 1, where n is not equal to a 0. And then I have number e. Number e, I wanted to have, let's say I have f of x, and f of x is equal to cosine of x. And then my number f is going to be, I'm going to have f of x is equal to sine of x. And then I have, let's say g, and my g, I'm just going to say I have f of x equal to 1 over x. Let's say now from on this interval 0 to infinity. So I wanted to find a set of functions such that when I am taking their derivative, I get this function, and then b, when I'm taking the derivative of that function, I get this. What are the solutions to what I want to do here? So I have a solution here. So the first thing that I want us to realize, we are actually having f of x equal to 2x. So we wanted to find the capital letter f of x, right? Want to find this function such that if I take the derivative of this function, I get 2x. So that is what I want to find here. If you look into this function, it is 2 times x, and we have 1 here. So this one here is a power function, and you have this 2, which means we are actually stretching this function a couple of units. So what is actually happening here? An antiderivative is an opposite of the derivative. So if, let's say, I was having a function, I'm just going to make an example here. I had my function g of x, and this function, let's say it was x to the power 7. To find the derivative of this function, I am supposed to just bring this 7 down, right? And then multiply by x, and then I have a 7, and then I subtract a 1. That is actually what is supposed to happen to get the derivative of that. Now, how do we get this function from that function? We need to reverse what we're doing here. We took the exponent, we multiplied by it, and then we subtracted a 1. So what we are actually going to do here to find the antiderivative of this nice power function, we will keep this constant as it is. We will have this 2, and then we're gonna have this x. Remember that to get this thing here, what we are going to do, we subtracted a 1 there, right? We first took the 7 down, and then we subtracted a 1. So what we are going to do to get that 7, because we will end up getting a 6, we need to add a 1 in that exponent so that we can remove that negative 1. So we have a 1 here, which is this one. So we will add a 1, and then we will divide, because we're multiplying. The opposite of multiplication is division. So we will divide by the new exponent, which is 1 plus 1. And then the next thing that you must realize is that if there was a plus, let's say here there was a plus 7 or plus 8, you must know that we're going to end up getting a 0 here, because the derivative of a constant is a 0. But here we don't know what was the constant of this function, that when we're taking its derivative we ended up getting this plus 0. So we say we are having some constant c, which means that that c can be a 7, a 5, or anything, because when I'm taking the derivative of this, I will end up having a 0, but it's not said here. And then we simplify here. Then when we're simplifying, we'll end up having a 2 times x raised to 1 plus 2. 1 plus 1 is a 2. And then we have a divide by 2 plus c, which is a constant of integration. And then this 2 and that 2 cancels out, and you have a 2 plus a c. And then we have f of x. So you will notice that if I'm taking the derivative of this function here, I will get this 2 will come down, and then subtract a 1, and I will get that part. And then the derivative of a constant is going to be 0, and there's nothing there, which means there is a 0 there. This is the most general antiderivative. This is what they were looking for. Most general antiderivative. And then this part here alone is the one that we call it a particular antiderivative. So I want you to see the distinction here, that this whole thing here, which was being asked from us, this whole thing is the one that we call it the most general antiderivative. So this is the answer we're looking for. I'm just specifying that this x squared is the one that is a particular antiderivative, and this is a constant of integration. Let's look at number B. Number B, we are having our f of x, and our f of x is equal to 3x squared. So we wanted the most general antiderivative. Of course, we use capital letter to say we're having an antiderivative, and then after that we keep the 3 as it is. We have this x. I want you to notice something here, that this one here is a power function. So because it is a power function, what we need to realize here is that in order to get this function, we had an exponent here and we brought it down and then subtracted a 1. So we had an exponent such that we subtracted a 1. So let's add a 1 to undo what we did, and then we brought the exponent down, we multiplied by an exponent. Let's divide by this new exponent so that it removes whatever was there, and then plus the constant there. So this antiderivative is going to be 3 times x raised to 3 divided by 2 plus 1 is going to be a 3 plus a c. And then we are having this 3 and that 3 is going to cancel out, and you have x cubed plus c. And then this is actually going to be the most general antiderivative. And when you are taking the derivative of that, you are getting that exactly. And also another thing, this here is the set of all functions such that when you are taking their derivative, you are getting this thing here. The reason I'm saying that is because this c can either be 1, can be 2, can be 0.5, can be 10, can be anything. So the choices of c that we have many of them. So this is not one function. We can either have a function out of this to be x cubed plus 1, or we can have x cubed plus 1 over 2, or we can have x cubed plus 7, or you can see that we have different choices. That is why I'm saying this is a set of all functions such that when you're taking their derivative, you are getting that. You can see when you're taking the derivative of this, you will get that. When you're taking the derivative of this, you will get that. And when you're getting a derivative of that, is that. That is why we're saying this is a general. In other words, it is the most general, and only this part, this one is a particular antiderivative. I hope you can see the difference that I have actually made, that we are having this as the most general antiderivative. And our c we're having f of x equal to 4x cube. Of course, capital letter f of x is just going to be, we still keep the 4 as it is, and then after that we have x, we have 3, you add a 1, and then you divide by that new exponent, which is going to be 3 plus 1, and then plus the constant of integration, because we're looking for the most general, not the particular, because the particular is only this part here. And then you can see that you're having a 4, and then you have an x. Of course, 3 plus 1 is a 4, and then divided by a 4 plus some c. This 4 and that 4 will cancel out, and we have x to the power 4 plus a c. And if you look into this one here, if you are taking the derivative of this, of course, you are getting that, because the derivative of a constant is just going to be 0. That is what is happening here. Let's look at number D. Number D, we are having f of x. F of x is equal to n. We have x raised to n minus 1. And we are claiming that our x, our n, we don't want our n to be equal to a 0. So when you are having that, we are looking for the antiderivative of this. You can see that we are having a power function here, so you keep that constant as it is, and then we want to deal with this part here. So we are having this n minus 1 now, and we had an exponent that was here, but we multiplied by it, right? And then we subtracted a 1. So we wanted to oppose what we did. So the first thing that we're going to do, we will add a 1, and then we will divide by this new exponent, which is n minus 1 plus a 1, and then we have that constant of integration, because we don't know. It might happen that it was a 0, 5 or anything, but it must be there, because we don't know what was that constant that was there. And then if you look into this, we have n times x, and then n minus 1 plus 1, this one is going to 0, so we have an n there, and then the denominator minus and 1, they cancel out, and you're left with n. This n and that n will cancel out. Of course, we still have a c, so this is going to be x to the power n plus a c. That is the most general. So if you look into this function here, when you're taking its derivative, you bring the n down. Take note that if you take the derivative of that, you get n, and then you have n minus 1 there, and then that's it. So when you're taking the derivative of that, and if you note this, it was the power rule that we were using when we were finding the derivative. And this thing here, it is the same as this. So when we were finding this, we were undoing the derivative, so we end up getting it as nice as it is. Number E. Number E is saying we are having our f of x is equal to cosine of x. So what is the function such that when I'm taking its derivative I get that? We know that the derivative of sine is cos, so the antiderivative of that is going to be sine of x plus some constant. That's how easy this thing is. And then we have our f, and our f is saying we have f of x. Our f of x is equal to sine of x. So what is going to be the most general antiderivative of this? We know that the derivative, let me use a different color here. We know that the derivative with respect to x of sine of x is equal to cos of x. So the particular antiderivative of this is supposed to be sine. That is why we're having this sign here plus a constant. The derivative with respect to x of cosine of x, we know that this is the same as minus sine of x. That's what we know. So the antiderivative of this minus sine of x must be cosine of x. That's the only thing we know. What does that supposed to mean here? If you look into this function here, I am actually having minus times minus sine of x. So this minus is the same as just a minus 1. So I'm going to pull the constant minus 1 out, and then after that I am dealing with this. What is the antiderivative of minus sine of x? We know it's cosine of x. So here we'll have cosine of x plus the constant. Of course, this antiderivative is just going to be minus cosine of x plus a c, because the derivative of cosine we know is going to be minus sine. Minus sine times this minus sine will end up getting a positive sign. That is fine, and the derivative of that. That's how easy this thing is. And then lastly, we're having our g, and g is saying we are having f of x, and our f of x is 1 over x. And of course, this one we know that it is defined from 0 up to infinite. Of course, the negative can be plugged in, but this one is specified for a purpose. We want to find the antiderivative on this particular condition. Now, what is the function f of x such that when I'm taking the derivative of this function here, we end up such that when I'm taking the derivative of this, I get that. That's what I want to say. Now, let's look into this here. There are some people who wanted to say that if we are having this one here is the same as minus x, and then after that they want to say, okay, the antiderivative is going to be x minus 1 plus a 1, and then you are dividing by minus 1 plus a 1. If you are actually doing that, you end up having a 0 here and a 0 in the denominator, which means this is actually not the correct way of doing it, because we know that whenever I am taking the derivative with respect to x of the natural log of x, when I'm taking the derivative, I always get 1 over x. That's what we know from derivatives. So the antiderivative of this, or the particular antiderivative of this, is supposed to be ln of x. So we'll end up having ln of x, or the natural log of x, plus some constant. That is actually what we're supposed to end up getting in this particular case. So these are some of the examples that we actually end up taking in this particular lesson that we're talking about, because we are focusing more on antiderivatives. I hope you are getting what we are doing here, and you're also getting the reverse of the power rule of derivatives, and we'll look at other rules. Don't worry about it. For now, let's just look at the table of differentiation formulas. Let's look at that. So we are having this table of differ differentiation formulas. Of course, this side I want us to have a function, and then this side I want us to have a particular. So we have a particular. This one is so close. Right here, a particular. So we have a particular antiderivative. So we're having these two things as only those two things, and then of course we can run from here and go down Let me end there. So if let's say I'm gonna use a black. If let's say I have a constant times some function f of x, to find the particular antiderivative of this, I keep the constant and I just find the antiderivative of this portion here. So I have the antiderivative of that. So we're done with that. And if let's say I have a function f of x plus a function g of x, and if let's say I am actually having two functions being added and I want to find the antiderivative or the particular antiderivative of this whole thing, I can just find the individual antiderivative, the antiderivative of that, which is f of x plus g of x, and add them. Even in the case whereby I have my f of x minus some g of x, of course I can just find the antiderivative of that, and then I subtract g of x, the capital letter g of x. That is that. The second thing, if let's say I have a function, let's say I have a function h of x is equal to x raised to n, whereby I know that n is not equal to minus 1, then the antiderivative of that is going to be x raised to n plus a 1, and then I divide this whole thing by the new exponent n plus a 1. So these are the particular antiderivative of that. And if you are looking for the most general, of course you just add a constant in each of these things. And the antiderivative of 1 over x, of course that one is supposed to be a natural log of the absolute value of x, because we know that the natural log when x is negative is not defined. So if we want to define it everywhere, we need an absolute value. But here the reason we did not need an absolute value is because we're only looking on the positive side of the x. So that is why we ended up just having this one here. But if it's not specified, then we know we must have that. And if you look into this one, remember that if you're having x raised to minus 1, in other words, if n is equal to minus 1, we end up getting this. That is why it's not part of this, because we are not going to end up having this format when we are having this, because this one is the derivative of a natural log function. So that is what is happening. The next one is the antiderivative of e raised to cx is the same as 1 over c times e raised to cx. Why is that so? Because this one here, where c is a constant, this one here, when you're taking the derivative, we'll take the derivative of this, which is going to be the same thing, times the derivative of the exponent, which is just going to be c. So that c and c will cancel out and you will be left with that. So the antiderivative of that is that thing over there. The antiderivative of cosine of x, we know that it is sine of x, or the derivative of sine is cosine of x. And another thing here, you have to also note that if let's say I am taking the derivative of minus cosine of x, then the derivative that I'll end up getting is sine of x, or the antiderivative of sine of x is minus cosine of x. And if let's say now I'm looking at secant squared of x. This one was a derivative of tan of x, if you remember when we're doing these nice things here. Let me also expand this a little bit. And then the next thing is, we also said when you are taking a sec of x times tan of x, this one was actually the derivative of sec of x. So this was the derivative of that. In other words, this one is the antiderivative of this thing here. The next one is, if you are actually having, because this one is just the last one here. So if let's say you are having 1 over, I have 1 plus x squared, it is actually a derivative of tan inverse of x. Of course, we also have cos inverse and other things. Of course, you can prove these things because can we try it? Because I don't think we took a derivative of this thing here. Okay. Just a quick overview. Suppose we wanted to find, suppose we have y is equal to tan inverse of x. What does that supposed to mean? It means that we are having x equal to tan of y. That is the meaning of that thing here. And if you want to actually find the derivative of this thing here, there are two things that you need to do. The first one is you just need to take the derivative on both sides, because we cannot, if you are making, we don't know the derivative of tan of tan inverse. So in order to prove if this is actually true, we just need to take derivative on both sides, because we know the derivative of tan, it is sec squared x. So what you actually do in this particular case, you just say, I want to take the derivative on this side, and I also want to take the derivative on both sides, derivative with respect to x of tan of y. And of course, if you look into this one, you will get a 1. And if you look into this side, if this one was y, this was going to be just sec squared y. But now this one is x, so we have to take the derivative of the inside using implicit differentiation. So we'll end up having here dy dx. We took the derivative of this, assuming this was x, we ended up getting that. But now we have to take the derivative of the inside, which means now dy dx is simply going to be 1 divided by sec squared y. That is actually the derivative. In other words, we have our y prime is equal to 1 over sec squared y. So this is the derivative. Now, how come now we end up getting 1 and 1 plus x squared, but here we're having sec squared? Is that even true? Let's just look into this. So what is basically happening here is this thing here. So if let's say we know this, let me go close to what is happening here. Where's this? From this part here, we had our x is equal to tan of y. So if you look into this, if let's say I was having a right angled triangle, we know that tan of x, let me put this, tan of theta. I'm going to choose an angle here. Tan of theta is the same as opposite over adjacent. So when you look here, we are having a 1 there. The angle is actually y in this case. So we're having our angle, which is y, which means this side here is going to be at the adjacent. Adjacent is 1, and then opposite is x, so the opposite is x, what is going to be that side. So if you are looking at this side here, of course it's going to be the square root of 1 squared plus x squared. That is going to be this side using Pythagoras theorem. That is what is happening. The next thing that you want to realize in this whole thing is this. I can find my sine of y here. My sine of y, we know that is going to be opposite over hypotenuse. It's going to be x over square root of 1 squared plus x squared. And then if I'm looking for cosine of y, of course it's going to be adjacent, which is 1 over, and then hypotenuse is going to be 1 squared plus x squared. And then if I'm looking for sec of x, no, sec of y, okay, let me first deal with that. Sec of y is the same as 1 over cosine of y. That's what is important here. And of course 1 over is just changing a numerator and denominator, so it's going to be just the square root of 1 plus x squared. And if, let's say, now this is actually sec y squared, so it's going to be that. And if you look into this thing here that we're actually doing in this particular case, you will actually end up finding that we are having 1 over we have sec. Okay, let me not write here. Let me just write here. So we have 1 over sec of y, and then this squared here is this squared there, and then I know that this sec y, I just found it here, that it is the same as 1. It is the square root of 1 plus x squared, because 1 squared is the same as 1, so it's 1 over 1 squared. And then if I'm multiplying, I mean I have this square, I have a square root, so these two will undo each other. That is why we end up having our derivative as 1 plus x squared. I hope you can see how we ended up having this. The derivative of this is that it actually revolves around this triangle here, which is nice. And then also understanding implicit differentiation. In most cases we don't usually go and do the sine inverse, cos inverse, and others. This is one that is much more popular in this course, but if you're doing pure maths, we're going to do all of them. We only focus on this one in this course, so we end up there. I hope you can see what is happening, because these are actually, this is the table that you need to know by heart, that we apply these rules. You must know these things by heart, know all of them. The reason we are looking into this one is because this one can actually even help you, even if you are looking for the antiderivative of 5 raised to maybe 2x. So once you know this one by heart, it's easy for you to convert this base and use e instead. It's going to actually help you. So that is why you need to know that. Let's look at a couple of examples, and then we close this lesson and we talk about something else, of course in a different lesson, not this one. So I have an example here. This example is saying this. I have this example. This example is saying find all functions g such that g prime of x is equal to 4 times sine of x plus 2x to the power 5 minus square root of x, all divided by x. So what is basically happening here? We wanted to find all the functions g whose derivative is this. So that is what we're looking for here. So the solution is not that hard here. We have a nice solution. So in order to deal with this, the first thing we need to realize here, we are having this g prime of x. It is 4 times sine of x plus 2x to the power 5 all over x minus square root x over x. And the next thing I also want you to realize in this whole thing is that this is the same as sine of x. When you're having one denominator, it means that this denominator is a denominator for that, and it is also a denominator for that. That is why I was splitting it like this. And also to move from here to there, you having a common denominator. That is why we take it as one denominator. I hope you can also notice that there. And then the next thing that I'm going to do, I have 2x to the power 5, and then I have an x minus, I have x raised to 1 over 2 all over x. That is what is happening here. I am still trying to simplify the derivative. I haven't started to look for the antiderivative at all. I'm still simplifying this. Why am I doing so? I want to make sure that here I'm actually having a power function so that I can deal with it easily. So I have 4, I have sine of x plus, and then when dividing powers of the same base, what do? You actually subtract exponents. So you will have a 2x raised to 5, and then I'm going to subtract a 1, and then minus x raised to 1 over 2. I'm going to subtract a 1 because of the denominator. And of course you can see this is 4 sine of x plus 2x to the power 4 minus x. When I'm subtracting 1 from this, of course 1 is the same as 2 over 2. 1 minus 1 is going to be a minus 1 over 2. I take one denominator there. And then I am having this nice function. So to get the g of x, this I'm looking for actually the most general antiderivative, because when we are saying find all functions, we are actually asking you find the most general antiderivative of this function. That is what is happening here. Of course, I am going to keep the 4 out. Now, what is the antiderivative of sine of x? You go back to the table and then you look at it. So I want the antiderivative of sine. So sine is minus cos. The antiderivative of sine is going to be minus cosine of x. So here we'll end up having minus cosine of x and plus, here I have a 2, I have x, I have a 4, and of course because this one is a power function, I just have to add a 1 there and then divide by 4 plus 1. That's simple as it. Minus x raised to minus 1 over 2, I have to add a 1, and then I have to divide by minus 1 over 2 plus 1. That's simple at its best. So this one is going to be minus 4 times cosine of x, and then plus, and then if you look carefully into this, I still have a 2, I have an x of 4 plus 1, that is a 5, and then divide this whole thing, 4 plus 1, that is a 5, minus. And then if you look into this one here, I'm actually having an x raised to minus 1 over 2 plus 1. That is the same as minus 1 over 2 divided plus 2 over 2. 2 minus 1, that is actually a 1. So we have a 1 there. And then we take one denominator, I have a 2, and then divide. Of course, whatever this is, it is actually the same as 2 over 2. 1 is the same as 2 over 2. Why am I using 2 over 2? Is because of this 2. I want to have a common denominator. 2 minus 1, that's actually a 1. And then I take this one 2. And then if I finalize, now I have minus 4 cosine of x plus 2x to the power 5 all over a 5. And then in this case here, dividing by this, I have this division. I can change this to multiplication. When I'm changing it to multiplication, I switch the numerator and denominator. That is why we're having a minus 2 over 1 x raised to 1 over 2. And of course 1 over 2 is just the same as the square root of x. I hope you can actually get to see how we ended up getting this. But now, if you look at this question, it said find all or the most general antiderivative. we need to end up having that constant throughout. Don't forget that constant, because you end up losing marks. It needs to be there. That is what is important in this particular question. Let's take another example here. Let's take another example. So this example is saying find f. Let me just say find the function f if the first derivative with respect to x is just equal to e to the power x, and then you have a plus 20, and then you have 1 plus x squared, and then I have a minus 1 there. Of course, I want the solution here down here. I'm looking for a solution. So what is this gonna be? Okay, so this one here, I want you to realize that this is the same as e raised to x plus 20 times 1 over 1 plus x squared, because a negative one, it means that this whole thing is in the denominator. So our f of x, because find the function f, so we don't know the constant, there's no other information, so we are looking for the most general antiderivative in this case. A derivative of e to the power x is just going to be e to the power x. In other words, the antiderivative of e to the power x is just going to be e to the power x. That one is still not gonna be changed. And then when it comes to this one, which is that, we're gonna keep the 20 as it is. And then what is the antiderivative of 1 over 1 plus x squared? So you come here to the table as I gave you, and then you look at 1 divided by 1 plus x squared, which is tan inverse of x. So we are actually having here a tan inverse of x. But now we also need that constant of integration. That's how easy this thing is. It's not that hard. This is actually our f of x. Let's look at another example. I want us to have as many examples as possible so that we can actually understand what is going on. I'm going to give you two questions now. The first one is saying find the function f, right, if its second derivative with respect to x is given by I have 12x squared plus 6x minus a 4, and we are also given the initial condition here, which is equal to a 4, and then we have that, and we are also told that if we are plugging f of 1, we're getting a 1. We want to find the function f. The second question, I'm gonna leave this space here and then write the second question here. The second question is saying a particle moves. It moves in a straight line, So we have a particle that is moving in a straight line. It has acceleration. Hope my spelling is correct. It has acceleration at time t in seconds given by a of t is equal to, I'm going to say 6t plus a 4. We have 6t plus a 4. This is a capital letter. Its initial velocity is v of 0 is equal to, I'm gonna say, minus 6 centimeters per second, and its initial displacement. Each initial displacement is s of 0 is equal to 9 centimeters. Find its position. We want to find its position function, s of t. So I want to find that function. Let's start with this question here. Usually, I want to specify this. This example can be rephrased, and someone would say, solve this initial value problem. I want you to know that when someone is saying find f of x, I mean f of x or just f, given this f of something is the same question as solve this initial problem. So it's one and the same thing. And also here it solve this initial value problem because they want you to find this position function. Okay, now let's talk about the solution of these problems. Solution. And of course, I think that is actually going to be the last questions or last examples, and then we'll start talking about something else. Okay, now this is the second derivative. So the first derivative of this function is going to be the antiderivative of that function, the most general antiderivative of that. So let us first find f prime of x from fw prime. In other words, the antiderivative of this, the first antiderivative of that. So how do we get it? Because this is just a nice polynomial. We keep the 12 as it is. We have this x, we have a 2, we need to add a 1, and then we divide by 2 plus a 1. And then plus, and then we're going to have a 6, and then we have an x there. Because there is a 1 there, we just need to, we have a 1, we need to add another 1, and then we divide by 1 plus 1. And then we go for this one here, plus we keep the 4. And also I want you to notice here that when there is nothing, you have an x raised to 0. So which means here you have an x raised to 0. And then now we need to add a 1. And then we divide by the new exponent, which is 0 plus a 1. And then of course, after that, you need to have a constant. Let me use C1 here. Why am I using C1 in this particular case? Is because I know that I will have to take the antiderivative again to get to f, because this is a second derivative. So I want to undo the derivative twice. So this one is the constant we get for taking the antiderivative for the first time. So our f prime of x is going to be, we're still gonna have a 12 times x raised to 3 all over, because 2 plus 1 is a 3, 2 plus 1 is a 3, so we're having a 3 there, plus a 6 times x raised to 2 all over 2, plus 4 times x, of course 1 plus 0 is just a 1, and then 1 plus 0 is just a 1, so we're just having a 4x here, a nice 4x, plus c1, we don't know that constant here. And then the next thing that we need to do is just simplify. 12 divided by 3, that's just 4x cubed, plus 6 divided by 2, that's 3x squared, plus 4x plus some constant c1. Let me add a page after, so that I can continue on it. And then the next thing that I want you to realize here is that when there is no x, you must know that there is x, but it's raised to exponent 0. So x raised to an exponent 0, we know that this is a 1. The reason I'm adding that is because I want us to also proceed to knowing that now we're looking for f of x. F of x is going to be the antiderivative of that. So we are going to keep a 4. we have a x, and then we have to add a 1 there, and of course we have to divide by the new exponent, plus a 3x, I have a 2, I add a 1, and then I divide by the new exponent, plus 4, I have x, there was a 1 there, so you have 1, I add a 1, and then I divide by the new exponent, and then I have a plus, I have a c1, and then I have x, I had a 0 plus 1, and then I have to divide by 0 plus 1 there, and then because this one is an antiderivative of that, I don't know what was the constant, so I'm going to say this is the second constant of integration, because I don't know what that function is, but I know that if I'm taking the derivative of this will go away and I'll be left with that, and this one, because this was a constant, it went away. I don't know what was that constant. We will find out. And then of course I can simplify further. I will have a 4, I have x raised to the power 4 all over 4, plus I have a 3, I have x raised to the power 3 all over 3, I have plus, I have x, I have 4, I have x, I have 2 divided by 2, I have plus, I have c 1, and then I have x 1 plus, as 1 0 plus 1 is a 1, 0 plus 1 is a 1, so we're having that, and then I have a plus c2. The next thing is to simplify further. 4 divided by 4 goes away, we have x to the power 4, and then 3 and 3 goes away, we have x to the power 3, and then when it comes to this one here, we are supposed to end up having something that is what did I do here? This one here was a minus. It was a minus. So at this position here, this was supposed to be a minus, this one was supposed to be a minus, this one was supposed to be a minus. That's a minor mistake. And then of course we're supposed to end up having a minus there, and then of course here also supposed to end up having a minus. I think so, because of this here. I don't want to make mistakes. Of course it's a minor mistake that will cost you some marks. So when it comes to this one here, of course 4 divided by 2 still have a minus. 4 divided by 2 is still a 2, and then we have x squared, and then we have plus, we have c1x plus c2. This is actually the original function, but what is that constant? That is where these given conditions, this condition and that condition, comes into play. So when I'm plugging in 0 here, f of 0 is going to be 0 to the power 4 plus I have 0 to the power 3 minus I have 2 times 0 squared plus c1 times 0 plus c2. So if you look at this one, this is 0, this is 0, this is 0, this is going to be 0. Whatever the value of c1 is going to 0, we're left with that. So f of 0 is equal to c2. But I know from this statement that f of 0 is equal to 4. So this one is supposed to be 4, which simply means that our c2 is equal to 4. And therefore, our f of x is going to be the same as x to the power 4 plus x to the power 3 minus 2x squared plus c1x plus a 4. That is actually our function, but we also have this constant here. But I have also another condition here. F of 1 is equal to 1. So here I just need to plug in f1. So if I'm plugging in a 1 here, I'll get 1 to the power 4 plus 1 to the power 3 minus 2 times 1 to the power 2 plus c times 1, c1 times 1, and then we have a plus 4. And of course you can see here 1 to the power 4 is just 1. 1 to the power 3 is just 1. 1 to the power 2 is just 1 times 2, so we have a 2 there. Plus c times 1 is going to be a c1, and then plus a 4. 1 plus 1 is 2. 2 minus 2 is 0, and then we have c1 plus 4. So this is going to be c1 plus a 4. So our f of 1 is equal to that. But I know that f of 1 is just equal to 1, which means that c1 plus 4 is equal to a 1, or c1 is just equal to 1 minus a 4 because it was positive this side, so it is equal to that. And therefore we can conclude that our C1 is just equal to minus 3, which means that our f of x is simply x to the power 4 plus x to the power 3 minus 2x squared minus 3x plus a 4. So that is actually what we end up having in this particular case. So we're having these two minuses and we have a plus 4. That is what we're looking for. So one important thing is this: we were looking for the original function, we're given the second derivative, we have to take the first derivative. When we're taking, we have to find the first derivative, which is the antiderivative of that, but we have to add a constant because we don't know what was that constant. But we know that when you're taking the derivative of a constant, you end up getting a 0. That is why we have that constant. And then for the second time, we take the antiderivative again. We have the second constant. We use the given initial conditions to solve that. That's how easy this thing is. I don't want anyone to lose marks because of that. A particle moves in a straight line. It has acceleration at time t in seconds given by a of t is equal to 6t plus 4. Its initial velocity is v0 is equal to that, and its initial displacement is given by that. Find its position function. If you remember, the velocity was actually the first derivative of that, and the acceleration was actually the second derivative of the position function. So we're gonna do the same thing here. Our solution is going to be straightforward, of course. We know that if you are having this as a displacement, then our velocity with respect to time is going to be the first derivative of this. This one is a velocity. And then from there, you know that you can get acceleration. And of course, acceleration, we know that it is actually the first derivative of velocity. In other words, it is the second derivative of the position or displacement. So this one is acceleration. And then when we are looking at the jerk is actually the first derivative with respect to time of the acceleration, and in other words, it is the second derivative of the velocity time function, and of course it is a third derivative of the position. So this one is what we usually call a jerk. Not a jerk as a jerk, just a nice jerk. So that is what is happening when it comes to these things here. So now we are given, if we want to find this, given this, you just have to keep taking antiderivatives to get this side. But if you want to move from this one to that side, you keep taking derivative and go all the way down. That is what is happening here. So in this particular case, we are given acceleration time function, which is 6t plus a 4. Now we have to first look for the velocity time function, and the velocity time function is the antiderivative of that, which is going to be 6, and you have a t. You have to, because there is a 1 there, you have to add a 1, divide by the new exponent, and then after that you come for this one. Remember that when there is nothing here, you have x to the power 0, so you end up having 4 times x raised to 0 plus 1 divided by 0 plus a 1. Of course, we don't know what the constant was, so we end up putting a c1 there. The second thing that you need to do, you just simplify. You have a 6, and then you have a t, and then 1 plus 1 is a 2, and then you divide that by 1 plus 1 is a 2, plus I have a 4, I have x raised to 0 plus 1 is just a 1, 0 plus 1 is just a 1, so we have a 1 divided by 1 plus a c1. Of course, our velocity time function is going to be 6 divided by 2 is going to be 3t squared plus 4x plus a c1, right? And another thing that is actually given in this statement, let's go back, v0 is given as 6 centimeter per second. So I know that if I'm plugging in a 0 here, I'm supposed to get 6. So I'm going to plug in 0 here, I will get 3, 0 squared plus 4, 0 plus a c1. And of course, I know that this is going to be 0 go away, this is going to be 0, so v of 0 is going to be c1. And our c1, we know that our v0, it was given there in the statement. v0 is minus 6, so this one is supposed to be minus 6. Therefore, c1 is equal to minus 6, which means the velocity time function is equal to 3t squared plus 4x, not 4x. Why am I using x here? This is supposed to be t. This one is supposed to be t because we are using a t here. And of course, the mistake I made, it was here. This was supposed to be a t, and this one was supposed to be a t. My apologies. This is supposed to be a t because this is the variable is t, not x. I just got hung up with my surname here because it has an x to it. Of course, my name also has an x, so I like these x's. So I always put this thing there. And then, of course, this one here, we ended up having a 6, and then this is actually the velocity time function. The next thing that you need to do now, you need to find the displacement time function, which is actually the antiderivative of that. So you will end up having a 3, and then you will have to add a 1 in the exponent, divide by the new exponent, plus a 4, you have a t, you have a 1, and then you add a 1, you divide by 1 plus a 1, because there is a 1 there, that this is the 1, and then you add another 1. And then we have a minus 6. Of course, here we had an x raised to 0, so you will end up having an x raised to 0 plus 1 all over x, new exponent, which is 0 plus a 1. And now we have a constant here, so that when I'm taking the derivative, I know that I will get that. And I don't know what that constant is because I'm taking the derivative for the second time. We usually place a 2 there, and this is a constant of integration. Then I simplify. I have a 3, I have a t, I have a 3, I divide by a 3, plus I have a 4, I have a t, I have a 2, I have a 2, minus I have a 6, I have an x, I have a 1, I have a 1, plus a c2. I can simplify further. This 3 and that 3, they cancel out. You have a t cube. 4 divided by 2, that's a 2t squared. And then I have a minus. Why am I using this x? I like this x. It's supposed to be just a t there. This is supposed to be a t. This is supposed to be a t. So this one is supposed to be a 6t, and then you have a plus c2. That is actually the position time function. The next thing, you go back there, you can see that you are given an initial position, and then we have to plug in the 0 there. So if we are looking for s of 0, we know that this is going to be 0 cube plus 2 times 0 squared minus 6 times 0 plus a c2. Of course, if you look into this, we have s of 0, and then this is 0 gone, this is 0 gone, this is 0 gone, so you have a c2. And of course, if you look into that given statement, this is supposed to be a 9 centimeters. According to this, supposed to be 9 centimeters, which simply means that our c2 is equal to a 9, and therefore s of t, which is this function, is going to be t cube plus 2t squared minus 6t. Now we have a 9, so we'll end up having a 9. This is what we're looking for. Just like with the derivative, you cannot get the second derivative without taking the first derivative. The same thing here. You cannot think that you will jump from acceleration to displacement, you have to first find this and then find this one from that. And also, if you wanted to, let's say you are given the jerk, you have to first find the acceleration, then from acceleration you end up getting the velocity, from velocity you end up going to the displacement. That is what I wanted to show you with these problems. And of course, I am going to end here. Let's hope you will actually understand this very straightforward, that actually the antiderivative is actually just taking or the opposite of a derivative, or undoing a derivative. That is actually what is important, and you have to know this table by heart. And more importantly, I want you to understand that this, we have a particular antiderivative, and we have the most general antiderivative. That one always end up having a constant of integration c. Make sure that you understand that. And of course, when you are given examples such as these, the most of the time when they are asked these questions, usually they are asked like this. We usually say, solve this initial value problem. That's what we usually say. Others find the function f of x, but it's the same thing, same process, and same final answer. Solve the initial value problem. When you're having f of something, they are telling you that this is the initial value problem. So just know that they are looking for this. So that is what I wanted you to understand in this particular example. I'm going to stop there, and then maybe in the next time we'll look at the we can just look at some of the examples of antiderivative and initial value problems, and then from there we'll look at sequence and series. Of course, we're not going to go too deep to that. We just needed to define integrals and also the area under the curve. That is what we will need it for. Of course, we'll look at arithmetic, not too deep, and the proof and all other things. We're not going to go too deep. We just need just to familiarize ourselves. Arithmetic, geometric, quadratic, and cubic. We're only going to look at these four, and then from there we can actually dive straight to it, to the area under the curve. And then once we move from the area under the curve, we can go straight to other interesting things on integration. But once we are done with the content, I will give you maybe just some questions. We do so many questions. Maybe you will be familiar with solving these problems. Again, like I said, when it comes to integration by parts, it's not part of the syllabus, so we're not gonna do that. If it happens that I ended up uploading a lecture on integration by parts, you can just look into it if you are still interested into it, but it's not part of the syllabus. So if you don't have time, you don't have to look into that one. It's not part of our syllabus. Like I said, we are not in the viewers sponsor scheme here. We just want to make sure that at least you get more help when it comes to these questions. That's all there is to it.